Okay, so we saw some examples in the previous videos of things that I may test you on or things that I want you to really take note of. And in this video, really what I want to talk about is like, how do we know that our regression equation is good? Okay, so let me change the colors because I'm over the green already. Let me choose this color. Let's do this purple one. Okay. Okay, so one of the things that you can do is you can find residual plots, and residual plots basically just plot the x values with the residuals. So remember, our residuals were all of our errors. So in the previous example, we found this number, right? That the difference between the true value and the predicted value was 1.7. So what we do, we plot the x value. So that x value was 2 and plotted with 1.7. And then you can see that this will be the one that you plot. So so that's one of the things that you can do. So you have here your actual regression. So here is the line, your data. Here is your residual plot. And the whole point is that you do not want to see a pattern. So if linear regression is appropriate, there must be a random scatter. So notice here there's no pattern. There is no pattern whatsoever. I don't see any pattern. You have to see it's legit pattern, like a parabola or something that will let me know that that linear regression will not be appropriate. Now, residual plots, these you can usually find in StatCrunch. You don't want to do this by hand. So these you can find in StatCrunch, and this is what we're going to work on next week. Okay, now, so I gave you 3 different types of graphs. Here there is no problem because you can see that all of my residuals and my residual plot is scattered. So this one's completely scattered. There's no pattern whatsoever. Here we see heteroscedasticity, which is what we were talking about also last week. If you see some sort of fanning, right? So if things are fanning, then you know that things are not okay. Okay, this is also not appropriate. Not appropriate. Okay, here was appropriate. This one was not appropriate. Here we see nonlinear stuff, things that are like curvature, right? So this is what we're going to call curvature, right? This also indicates that linear regression is not appropriate. So we have to use some other method, okay? So when we try to plot a line, well, sometimes a line may not be useful because if our graph looks like a parabola, then maybe we should apply some sort of parabola, okay? So this is what tells you that linear regression is not appropriate, okay? All right. Now, another thing that you can think about is the coefficient of determination. So this was the last thing. So if you go back to this one, this was our coefficient of determination. So this is when we're going to talk about this. So coefficient of determination, it's a little complicated to really explain, but the coefficient of determination just measures how much of the variation in the response variable is explained by the explanatory variable. So basically, how much of the y, of the variability in y, is explained by the x value. Okay, so for example, I gave you 3 different examples. So if you have an r² value of 0, that means that the y value, all the variability in the y value it's not explained by the explanatory variable at all, okay? If you have 0.5, that means that only 50% of the variability in y will be able to be explained by the variable, by x. Here, if you have r² is equal to 100%, I'm talking in terms of percentages, okay? And this was 50. That means that 100% of the variability in y can be explained by x. Now, what the heck does that even mean? Okay, so basically what that means, let's say I have x here. Here's my x. Let's say here's my y. I know that there's some sort of association between x and y because when I graphed it, I got some sort of linear curve. So I know that, that there is a partial cause between x and y, okay? There's a partial cause, and that cause can be explained with the slope, okay? So I know that for every increase in x, my y increases by the slope. So I know that I can explain it using that way. Now, the variability in y, so let's say my r² or my coefficient of determination, because r² is my coefficient of determination, was 72%. That means, okay, that 72%, so let's say this is 72%, that 72% of y, okay, that 72% of variability of y can be explained by x. That's all it means. So there is still some other amount, okay? So there is a 28% that is unexplained for. So if I were to graph this, okay, that means that I can explain a lot of these points, but there are some points outside that I cannot explain. I don't know what's going on here. This one I don't know. This one I don't know. I can only explain the things that I can correctly predict, I suppose. So don't waste too much, don't try to overthink this. It's a very hard concept. It just takes a little bit of a while to really understand. But how you calculate it, all you gotta do is just square the correlation. So if you have the correlation, just square it. If you have the correlation what did I do here? R equals plus or minus square root. Oh, if you want to find the correlation and you have the coefficient of determination, all you got to do is just square root it. Okay, so let me give you a couple of examples. Okay, so we conducted a regression for the width of books in terms of the number of pages. Okay, so whenever you see this, also if you see in terms of, the thing afterwards is usually your x value, and this thing is usually your y. Okay, so this is usually a keyword in terms of, that means that this is your x, this is going to be your y. Okay, so the correlation coefficient was r equals 0.9202. Find the coefficient of determination. Well, coefficient of determination means that you're looking for r squared. So it literally is what it's telling you to do. Just square the r value, square the correlation. So I'm going to take 0.9202, and I'm going to go ahead and square this. Okay, so I'm going to put this in my calculator, square it, okay, and you're going to get 0.847, okay, which is approximately 84.7%, okay, so that's what that is. Now, interpret it. So what exactly does this mean? Okay, so this is what it is. This means that 84.7% of the variation in y can be explained by x. Okay, so I can explain some of the variation in y by x, and I can only explain 84.7%. This is it. That's all you gotta write. Okay, so if you want to copy this down, copy it down. This is really what I'm really looking for. 84.7% of the variation in y can be explained by x. Okay, all right. So now let me give you another example. Okay, so given the following StatCrunch output, so I gave you the graph itself. So I was looking for, so you have some people that are drinking beer and they're trying to do a bullseye. So the more that you drink, you're probably not gonna score very well. Okay, so if the coefficient of determination is 78%, okay, find the correlation coefficient. So I know what r squared is now. My r squared, let me write it as a decimal, 0.78. Okay, so that's what my coefficient of determination is. Now my correlation is my r value, so I need to find r. So how do I get r? Well, I'm going to square root both sides. And when I take a square root, I also add a plus or minus. So r is going to be equal to plus or minus the square root, okay, of 0.78. In this case is 0.88, which is a strong correlation. Okay, now is it positive or is it negative? Well, if I look at the graph here, this thing is downward sloping, so it's going down. Okay, and you can see that whenever you have this, you probably have a negative slope. So I'm going to choose the negative sign. So r is equal to negative 0.88. That is how you find that. Okay. All right. Now I just put a little note here, and I put a warning. And this warning basically is, do not extrapolate your data. Okay, extrapolation occurs when you try to predict outside the range of data. So for example, if I was looking at, I don't know, if I was looking at height and I was also looking at weight, okay, I only have data that's between, I don't know, between 60 and 70 inches, right? I cannot predict what's going to happen to someone who's 60 inches. I do not know what that is. Do not try to do that. You only know what the data looks like here. You have no idea what it looks like here. Okay? So that's what I mean by extrapolation. So don't do that. Okay? And that is it.